Great, thank you. Hi, I'm Ernest. I'm a first-year PhD student at Cornell, and today I'm excited to talk to you today about Mica, which is a PPX extension that automates differential testing for OCaml's module system. This is joint work with Harry Goldstein and Benjamin Pierce at UPenn, supported by the National Science Foundation. Let's talk about modules. The ML module system allows for representation independence. This means I can have two modules, M1, M2, that both implement the same signature S. But M1 and M2 might implement S completely differently under the hood. Crucially, if I am a client of a module that implements S, I don't know whether that module's implementation comes from M1 or M2. All I know is that that module implements the interface described by S. Now, this is all very abstract, so let's look at a concrete example. Let's say we have a module signature S for finite sets. I have an abstract type, alpha t, and some functions for building and inspecting sets. There are several ways in which one can implement this signature. One way is to use lists, setting alpha t equal to alpha list, and making sure that my lists don't contain duplicates. I can also implement sets using binary search trees. I'm going to set alpha t equal to a tree data type, and here I have to make sure my implementation follows the canonical BST invariance. This raises a question from the perspective of a client of my set interface. Are my two implementations equivalent? Morally, does my union operation on lists behave equivalently to my union operation on BSTs? Specifically, the notion of equivalence we care about is observational equivalence, which informally says, given equivalent inputs, do the two modules give us equivalent outputs? But how do we check observational equivalence? Well, one way is to use property-based testing. This is a testing paradigm where instead of writing unit tests, we instead write properties, executable specifications that describe the desired behavior of our program. We then write generators, functions that produce random inputs of the desired type and shape. And then we check, do these random inputs satisfy our property? If yes, then we can conclude with high confidence that our implementation follows our spec. Property-based testing was popularized by Haskell's QuickCheck library, but similar tools exist in many languages, including OCaml. So why should we care about this? I argue there are two reasons. The first reason is that trying to test observational equivalence directly using existing property-based testing tools requires a lot of significant programmer effort. But don't take my word for it. In a recent ICSI paper, my co-authors talked to 30 OCaml developers at Jane Street about how they use property-based testing. And the Jane Street developers said that although property-based testing frameworks are a natural use case for differential testing, they said that having to write all the property-based testing boilerplate was tedious, overwhelming, and it posed a great cognitive overhead to them. In fact, in their ICSI paper, my co-authors argue that in languages like OCaml that have rich module structures, there should be automation surrounding differential testing of a pair of modules that implement the same signature. This is the very problem we set out to solve with Mica. The second reason why I argue you should care about this is that a lot of real-world OCaml code is written using multiple modules that implement the same signature. For example, the Mirage OS operating system, as you can tell from this figure from a Mirage OS paper. So that's all the motivation. This is the interesting bit. Now, what if I told you you can take two modules, M1, M2, that implement the same signature, and automatically get property-based testing code that tests them for observational equivalence. This is exactly what Mica does. Mica is implemented as a PPX compiler extension. What you do as the user is you take some module signature definition. Underneath it, you write this deriving Mica directive. Then at compile time, Mica automatically generates specialized QuickCheck code using Jane Street's QuickCheck library that tests the two modules for observational equivalence. Mica also gives you for free a test harness, which you as the user can instantiate with the two implementations that you care about. Specifically, at a very high level, what Mica does is Mica will generate expressions that represent operations exposed by the interface and tests that the two modules are equivalent with respect to that interface. So for example, if my two modules are my list and BST implementations of sets that we've seen, then Mica will randomly generate expressions that represent series of invocations to the functions exposed in the signature. Now, this is all a bit abstract at first, I understand. I'm going to talk about how this works in greater detail in the next few minutes. So what exactly is in the code that Mica derives? Well, Mica derives the following. Mica derives a few auxiliary data types, which I'll explain in a minute. Mica gives you a QuickCheck generator of random values. Mica also gives you an interpreter, which interprets expressions over a concrete module. And finally, Mica gives you a test harness for testing the two modules. I'll talk about how these bits fit together in greater detail right now. The first thing that Mica gives you is a data type expr representing symbolic expressions. The idea is that we are going to model operations exposed in the module signature using an inductively defined algebraic data type. So what Mica does is Mica walks over the module signature, and for every declaration it sees, Mica creates a constructor for this algebraic data type, where this constructor shares the same name, the same arity, and the same argument types. So you'll notice that the empty variable on the left corresponds to the empty nullary constructor. The isEmpty unary function in the signature corresponds to the isEmpty unary constructor on the right-hand side, and so on. At this point, Mica also performs monomorphization. So it replaces all variables alpha with int, following a well-known heuristic in the property-based testing community. Now, these symbolic expressions are typed. So Mica also produces an auxiliary data type called ty, representing the types that you might see in the module signature. This is just a simple enum. Mica also defines an auxiliary data type called value, which represents the subset of symbolic expressions that are values. Next, Mica automatically derives an interpretation functor, which takes as its argument a module that implements the signature that we care about. You can think of this interpretation functor as a big step interpreter. It takes some expr, some symbolic expression, and steps it until we get a value, interpreting it over the concretes module in the process of doing so. Next, Mica gives us a QuickCheck generator called genexpr. Genexpr generates random symbolic expressions of well-typed expressions. Crucially, genexpr is parameterized by ty, which is the type of symbolic expression that we expect. And genexpr ty promises to only give us well-typed symbolic expressions of type ty. This is an example of a well-typed symbolic expression, because we can take the union of two sets. That's good. This, however, is not good. This is ill-typed, because isEmpty expects a set as its argument, but size gives us an int. This is a representation of an ill-typed symbolic expression, and genexpr says, I will never give you such an expression. That's forbidden. Finally, Mica gives us a test harness functor, which is parameterized by the two modules that implements the common signature S. And you, as the user, can run functions in the body of this functor to test the two modules. Crucially, this functor only checks for observational equivalence at concrete types, such as int or string. We don't check for observational equivalence at abstract types, for example, alpha t. The reason for this is abstract types have an abstract notion of equality, which is different from OCaml's standard polymorphic equality. Take, for example, my set abstract type set.t. Set.t can be represented using lists and binary search trees. And it doesn't make sense to compare a list and a binary tree directly for equality, because that violates the representation barrier. Instead, this is why we only check for observational equivalence at concrete types only, because int looks the same in both M1 and M2. So how does all this fit together? Well, first, we're going to invoke our QuickCheck generator to get some random symbolic expression. We're going to then feed that symbolic expression to our interpreter, which interprets it over a concrete module. Our test harness then repeats this process over the two modules implementing the common signature, and then checks them for observational equivalence. So this is how the code derived by Mica works. Now I'm going to talk about some case studies where we use Mica to successfully catch bugs. Here are a bunch of data structures where we've tested Mica with. For each of these case studies, we've picked 2 modules that implement the same signature in completely different ways. Some of the more interesting examples include the regular expression matcher, where we use Mica to test a derivative-based implementation of regular expression matching versus one which uses finite automata to match regular expressions. The unsigned integers example is also interesting because we check that 2 libraries for unsigned integer arithmetic handle things like overflow equivalently. Specifically, across all of these case studies, Mica was able to catch 35 bugs that we inserted manually across these modules. And the bottom set of case studies is taken from 6 real-world OCaml libraries that we found on OPAM. Besides all of this, we have also replicated an existing case study from the property-based testing literature. How to specify it is an introduction to Haskell QuickCheck written by John Hughes, one of the inventors of the original Haskell QuickCheck. This paper uses as its running example binary search trees. In particular, the Haskell artifact for this paper contains 9 implementations of binary search trees, 1 of which is correct and 8 of which are buggy. These bugs are all different, and the bugs range from the subtle to the blatant. What we did was we manually ported this artifact from Haskell to OCaml as 9 separate modules, 1 correct module and 8 buggy modules, and then we checked, could we use Mica to compare the correct module against the buggy module and see if Mica could catch the bug? And it turns out Mica can catch the bug. Each of these bugs was caught within, on average, 170 randomly generated symbolic expressions. So this is great. We can tell that Mica can be used to catch bugs. Now, at this point, you might be thinking, oh, but you only have 8 bugs here. That's not a lot. Can you use Mica to catch even more bugs? To answer this question, we turned our attention to Penn's undergraduate Intro OCaml class, which 400 students take every semester. This is a natural source of bugs because undergrads are learning and writing OCaml for the first time. As homework, students were asked to implement sets 2 times, 1 using lists and 1 using binary search trees. And then we checked, could we use Mica to test where the students' implementations were observationally equivalent? I want to make it clear that we looked at historical data from a past semester. We did not change the design of the course for us to perform this experiment. And it turns out that Mica was able to catch bugs in 107 student submissions. That's nearly 30% of the class. Crucially, 91% of the bugs that Mica found were caught within 300 randomly generated symbolic expressions. What's even more interesting is that as homework, the students were asked to manually handwrite unit tests. And the students' implementation passed their own unit tests, but Mica reviewed an observational equivalence bug in their implementation. This suggests that an automated approach for finding observational equivalence bugs, such as Mica, can help facilitate more robust and comprehensive differential testing compared to just manually writing unit tests. So that's all the case studies we've tested Mica with. In addition, we have also taken some first steps to integrate Mica with Tyche, which is a VS Code extension that my co-authors have been working on for visualizing property-based testing effectiveness. My co-authors will be presenting Tyche at WIST next month. At a very high level, what Tyche does is Tyche will visualize Mica's test results, showing you how many observational equivalence tests passed and failed. Tyche will also illustrate the distribution of the random symbolic expressions, as well as timing information regarding the tests. Now on to future work. As future work, we'd like Mica to be able to support higher order functions if they're exposed in the module signature, such as map and fold and whatnot. We'd also like Mica to support imperative code. As functional programmers, we all know that whenever we introduce mutable states into a program, we open a can of worms. And this is still something we're actively still trying to figure out. One idea we have is to add an extra constructor called seek to our symbolic expression data type, where seek of E1 and E2 represents the sequencing of E1 and E2, where E1 is an operation that returns unit. So we can sequence it using semicolon. But this is just like some initial thoughts. We have some other thoughts on how to support imperative code, but this is all future work. Additionally, we'd also like to support differential testing of functors. What does it even mean for two functors to be observationally equivalent? This is still something I haven't figured out, so we'd love to tackle this problem in the future. Next, we'd also like to use coverage-guided fuzzing to guide Mica's QuickCheck generator, so that newly generated symbolic expressions tend to exercise previously untested code. There's a lot of work in the OCaml and Cork ecosystems that combine property-based testing and coverage-guided fuzzing to achieve this. And we'd like to borrow some ideas from them in the future. So to summarize, if you remember nothing else from this talk, remember this. Mica is a PPX extension that automatically derives property-based testing code for testing module observational equivalence. Today, I've shown you the design of our PPX extension. I've talked about some case studies where we use Mica to catch bugs. And I've also previewed the beginnings of a VS Code extension. That's all from me. Thank you very much.
Thank you. That was excellent. I didn't expect to see my unpublished paper to pop up there, but I expect we will have lots of questions.
Thanks for your talk. I'm very excited to use your library, but a lot of our modules don't bottom out in things that aren't abstract. What would you recommend we do? And have you considered going and looking for whether the things that are referenced in the leaves derive a quality or something, like something you can pull in order to compare?
Oh, yes, good question. By not bottoming out at something abstract, do you mean there are multiple mutually dependent abstract types that are defined across multiple signatures?
Yeah, exactly. Like in my signature, when you do the thing where you sub an int for tick A, what if we don't have anything like that? Like we have a subtyping lattice module that we want to re-implement, and type is defined somewhere else.
Oh, OK, great question. I have some slides in the appendix that might address this.
You ready?
OK, firstly, if we have like some opaque type T, then we expect the user to provide a QuickCheck generator called QuickCheck generator T. In the code that Mica derives, we will then call Jane Street's PPX QuickCheck macro to desugar that. So this will allow us to generate random values of types that Mica doesn't know about. But you are right in that Mica currently offers limited support if you have multiple recursive types, multiple abstract types that are dependent on each other and defined across several signatures. At the moment, Mica is just a research tool, so we haven't run into that situation in the examples we've seen so far. Talk to me if you'd like to contribute to Mica and make Mica the best differential testing tool for OCaml modules.
Thank you.
Thanks, a really nice talk. I was wondering, what does it look like when Mica finds a bug, and have you put any work into like minimizing those or producing the smallest representation of the bug?
That's a good question. What Mica presents when it finds a bug is it will give us an S expression of the expression that evaluates the different values when it finds the bug. You can see some examples of the S expression there at the bottom of the screen. Right now, we haven't really thought much about shrinking. We thought that's more of an engineering challenge, but we ought to think about shrinking if we want to make this a usable tool. Specifically, the challenge is to shrink in a type-preserving manner. If some expression has type tau, we want the shrunken expression to also have type tau. And because right now our symbolic expressions are extrinsically typed, we haven't really figured out a way to perform the shrinking in a type-preserving manner. But that's future work.
OK, thanks.
Hi. I'm surprised to see that the expr and types aren't parameterized by what they represent.
Very good question. I have a slide that addresses this in the FAQ. So it is possible to represent values and exprs as parameterized GADTs. And indeed, one can write an interpreter for these GADT representations of expr and value using like locally abstract types and all that. But I argue this is non-trivial and hard to get right on the first time. When I first tried to write a QuickCheck generator for this, I ran into a lot of bugs because QuickCheck, or rather the type checker, couldn't figure out how to unify different inhabitants of my GADT. And so I argued that trying to represent this using GADTs is possible and very hard. And Mica needs to do this automatically on the fly for any signature that it might see. This is why we settled for an extrinsically typed representation of symbolic expressions using regular algebraic data types.
Cool, thank you.
All right, thank you. I'm sorry we don't have time for more questions. Thank you again.